All right, so we've been working on the particle in the box problem. And so what do we call this equation here?
No, that's time dependent, sorry.
You jumped straight to where I was going, though. This is the time-dependent Schrodinger equation. And then we split it into a time portion and a non-time portion. And so we took that and we split it into, here's the time-independent one and the time-dependent version. And then we found solution for the time-dependent version that's always the same. The time-dependent version always has this solution. And so we're like, we're not going to go through that ever again. We've already done it once. We'll just slap that on to any solution we have for the spatial part. So then we went to the spatial part. And so for the spatial part, we have what we call stationary states, functions that aren't changing in time. And we're going to have a solution that is the linear superposition of each of the spatial solutions multiplied by the temporal time solution, and then multiplied by a constant to tell us how strong that solution is. And we're going to go through now, and today we're going to actually do that part. Because we have found these, we have found the energies, and so now we're going to go on to how we put them together. So here's a summary of the work that we did last class period. We went through and applying the boundary, well, first of all, applying Schrodinger's equation, we found the solution had the form of e to the bx. And that is differential equations, and I just gave you that form because you don't have differential equations. But what we did do is we took that and we put it into the Schrodinger equation, and we solved for what b has to be. Where in the process did quantum come into our quantum physics?
When we were finding what values the wave function could have, or what it was like the kx.
When we were applying the boundary conditions. When we were applying the boundary conditions, in order for our wave function to obey the boundary conditions, we could only have specific values of, well, remember the b, we replaced b with ik or k, depending on energy. And we could only have certain k values, which meant we could only have certain energies. And so our system suddenly became quantized. There are only certain energies you can have for a particle in a box with infinite walls. And so the n's are numbering the energy states. So we have psi, forgot to put the subscript of n here. I was so excited to put Roman numeral 2 because it was in region 2. I forgot to put the subscript in. And so that was a sinusoid, and the energies depended on n as well. So that's where we ended. And of course, we did normalize this. That's where we got this square root 2 over L term from, was from our normalization. That's the normalization constant. So that's where we ended. Now, do you have any questions about that process? Obviously, we're going to go through the process again with a different potential. Yeah, probably 3 more times. And then the class will be over. I mean class, I mean the semester.
With a different potential, meaning instead of having the boundary conditions with the particle in a box, we'll have a different set.
We'll have a different set of boundary conditions. We're going to end up with the boundary condition, well, not boundary conditions per se, but potential energy function. We're going to end up with the potential energy function for a hydrogen atom. That's what that'll be our final case.
So this was the easiest one because in this case we could just get the sine kx.
Yeah, so this is always your first application.
Will you always end up with a sinusoidal function?
No.
Okay.
No, you will not. And we'll see that in our coming up examples.
And is that because sometimes we don't use the Euler's relation, and other times we do?
Right. Well, it's more. Sometimes you have an e to the I k x, and sometimes you have an e to the kappa x without the I.
Okay.
If there's no I, you couldn't use Euler's relation.
Right, that's true.
And then there are some times when you're going to go ahead and leave it in e to the ikx, but that's more rare. Usually if it's e to the ikx, you're probably going to put in sine and cosine because we're just more comfortable there, right? You could do it either way, sine or e to the ikx. And, we could have done that here with e to the ikx as well. Okay. And, I am not so ignorant. I could have written, since sine of kx is, well, you know the definition of sine probably. There. There, I left it in the IKX form. But it would have been a lot harder to get here if I left it in the IKX form because we know sine is equal to 0 at. Yeah. And so it was much easier. Okay. And I believe it's over 2i, not. Yeah, it depends on, it could be a minus sign difference. All righty. So we're going to now move on from there. Somewhat. I thought I had right here. There it is. Okay. I just wanted to make sure that slide was there so I didn't forget it. The solutions we just found are what we call mutually orthogonal. Does orthogonal even mean anything to you? Okay, orthogonal. Okay, so one said yes, one said no. Orthogonal is the highfalutin, and by highfalutin I mean multidimensional version of perpendicular. So in regular old math, if you want to find if two lines are perpendicular, you do the dot product. If the dot product is 0, they're perpendicular. If the dot product isn't 0, then there's at least some portion that's parallel. So orthogonal is multidimensional. We are working with, how many solutions do we have for a Schrodinger equation? I'll back up one step here. How many solutions do I have there? An infinite number, because n only had the condition that it's an integer starting at 1 and going up, a positive integer. There's an infinite number of positive integers, so that's an infinite number of solutions I just found. And so we now are working in an infinite vector space where each psi sub n is a vector. And if they're mutually orthogonal, that means each vector has to be perpendicular to every other vector. And of course, in three-dimensional space, all of this breaks down, right? I can only have 3 mutually perpendicular directions in three-dimensional space. But this is an infinite dimensional space. I can have an infinite number of mutually perpendicular directions. Infinite dimensionality does not make sense in my mind. When I was in graduate school, as a joking sign of respect, we said that one of our teachers lived in Hilbert space. Hilbert space. I believe the space we're working in here, I get the names of the spaces if it's an Euler space or a Hilbert space or whatever. Confused, but that's where our solutions are residing. We have an infinite number of solutions, and each one has to be perpendicular. So how we test perpendicular is by doing a dot product. And you're like, okay, great, I can do a dot product. This is how we do a dot product. Psi star n times psi m integrated over all space. That's the dot product. If they're orthogonal, that has to be 0. So the first thing I'm going to do here is to check to make sure my solutions obey this rule. Our functions have to be orthogonal. That is, in the end, we're going to say we're this percent in this state, this percent in this state, and this percent. In order for a given state, each of those different states has to be orthogonal. They have to not be partially in the same direction going into a spatial equivalence. So was there a question?
What does that mean, going into a spatial?
Well, a spatial equivalent is using the spatial analog for the direction of a vector, right? Because I can, in my brain, I can clearly see 2 vectors in three-dimensional space. These are vectors in infinite dimensional space, and I cannot see those in my brain. So that's why I use the three-dimensional space for the seeing it in my head. So we're going to test this. So integral of psi star psi dx. Now it's from minus infinity to plus infinity, but our wave functions were 0 outside of the box. So I'll put here minus infinity to plus infinity, and I'll put n and m for my subscripts. That's going to be an integral that just goes from 0 to L because my psi and psi star were 0 outside of 0 and L. Is it very clear why I changed my limits here? Because if it's not, I need to make sure. Then I'm going to have psi sub n star square root of 2 over L sine of n pi x over L. And then I have my psi sub m square root 2 over L sine of m pi x over L. Oops, dx. And this x does not look very xy. There we go. So there I have rewritten it, and we want to actually calculate this integral. So to calculate this integral, well, I have two signs multiplied by each other. Does anybody have their trig relations handy? Do you really?
Yeah.
Awesome, because I didn't check it before class. I was going to have to look it up myself.
It is going to be sine squared x dx is equal to 1/2 x.
Well, no. Not the integral table.
Okay.
The sine A times sine B.
Oh, because you can't do a substitution.
Yeah.
That I don't have it.
I didn't either. So this is the kind of thing that obviously I should have memorized. But I don't. I'm sure it's somewhere in the textbook, but where in the textbook? We could figure it out from the back cover of the textbook because it gives you sine of a plus b and cosine of a plus b, but I'm just going to look it up. Sine A times sine B formula. Works for me. Of course, the first one I will go to doesn't show it. I think this one will. So sine, goodness, sine A sine B is equal to 1/2 cosine of A minus B minus cosine of A plus B. So there is our definition of what you get when you multiply two sinusoids together. And so with that, then I can take my specific example here and sine of n pi x over L multiplied by sine of m pi x over L is equal to, there's a 1/2 around this whole thing. So A minus B, that's going to be, everything has a pi x over L in it. And so I'm just going to put n minus m so there's the subtractive part. And then the additive part is going to be So if n and m are not equal to each other, that is, we're looking at two different solutions to check to see if they are orthogonal, then n minus m and n plus m are integers. What's the integer? I don't care. I could call this, j and k. I don't care. What do I have if I integrate cosine of some integer multiple of pi x over L from 0 to L? That is, and I will be very clear here. I have a cosine wave. So a cosine wave starts at maximum, goes like this. And we are going, if n minus m is equal to 1, then we're going to be going from that starting point to half a cycle to here. If it's equal to 2, we're going to be going to here. If it's equal to 3, we're going to there, and so on. What is the integral going from here to here? It's 0. You have just as much area above as you had below. And then each one is adding on the same thing. So no matter what n and m are, as long as they're not equal to 0, the integrals of each one of those dx from 0 to L is going to have to be 0. So I made my argument here logically instead of actually doing the math. I could have done the math, integral of cosine is minus sine, and then you put in your limits, and you're going to find it 0. But to me, it's more fulfilling to actually think about what it means and look at the graph. So the integral, notice square root 2 over L times square root 2 over L is going to give me 2 over L out front. And then I had 1/2 cosine, and I will do like I said, j pi x over L minus cosine of k pi x over L dx from 0 to L is going to equal 0. And like I said, you can go ahead and you can put in the sign and put in the limits, but it's equal to 0. So what did I show? I showed that yes, indeed, as long as n is not equal to m, that they're going to be orthogonal, that the integral of psi n star psi m is 0. Well, that's beautiful. But we also have the condition that these wave functions have to be normalized. And so if n is equal to m, right, same integral except for n is equal to m, then it's got to equal 1. It's got to be normalized. Now, of course, it makes sense. If we're doing a dot product, if we do a dot product of an item with itself, it better not be 0, right? It can't be perpendicular to itself. So it has to have a finite value, and then our normalization condition is the one to make it 1. So we've already gone through the normalization calculation, so I don't need to repeat the normalization calculation. That was the one with the sine squared that you look up in the integral table, right? And so this condition in the blue, soon to be in a blue box, combines the mutually orthogonal requirement of our solutions and the normalization requirement of our solutions. And so we call that equation in the box the orthonormal condition. Orthonormal means that each one of our solutions are normalized and mutually orthogonal to all the others. Now, just backing up to the beginning of this slide, what does orthogonal mean?
Well, basically they're perpendicular, but in 3D.
In more than 3D, in any dimensionality. That's right. So the dot products are 0. This here is the calculation of the dot product. This thing right here is called the Kronecker delta. You can see the spelling of Kronecker at the top of the slide. The Kronecker delta is a fun little symbol. It has two indices. If those two indices are the same, then its value is 1. If the two indices are different, then its value is 0.
Indices?
Yeah, indices is the plural index. So n is index, m is index, and then another indices. In today's world, people would probably say indexes, but that's just wrong. That's like saying, yes, I was writing on the different forms. You don't take offense at that?
I would say that as well.
The textbook has 3 appendixes.
Which sounds wrong.
It is wrong.
I just want to know what else to say. I'm not disagreeing with you.
Okay, anyhow, I always like to point out these stupid things. Here's a stupid thing for me to point out. This building was named after, I can't remember her first name, Kruger, the lady who died a couple months ago. And Union College put out a PR blurb that she was an alumnus of Union College. Alum would have been fine. Or alumna would have been technically correct. Because alumna is a female graduate. But alumnus is a male graduate. And so I quickly sent a message to the head of our PR, that's a pretty basic mistake we have here that probably should be rectified before it goes out too far. And her response was, here at Union College, we have decided that alumnus covers all genders.
I don't know if that's your call.
Yeah, that's exactly what. I'm not going to go argue with you, but yeah. I don't think you have the power to rewrite Latin rules. Okay, so back to this. So this equation here with the Kronecker delta means that if n is not equal to m, this integral is 0. If n is equal to m, this integral is equal to 1. So it's a very meaningful equation. It's one of those ones that we have to have. So orthonormal, remember that word, especially tomorrow.
Can you repeat again the orthonormal condition?
Well, the orthonormal condition is the thing in the box here. It's that equation.
Okay.
And so that means that the solutions to the Schrodinger equation must be normalized and mutually orthogonal.
And instead of saying solutions to the Schrodinger equation, could you say wave function? Like psi of
yes, the wave functions, yes.
Okay.
Or the stationary states.
Okay.
We have a lot of the eigenfunctions. There's another one you could have used.
Oh, I feel like if I say it in a different language, it can't be wrong.
It can't be wrong. That's my go-to. All right. Now we have completeness. Completeness is another linear algebra idea. We have to have if you think about it, each of our wave functions, our eigenfunctions, are normalized. So they're vectors with a magnitude of 1. Each one of them are mutually perpendicular, mutually orthogonal. So if we were to put this into our spatial, the way we do calculations in space, we would say these are our unit vectors in each direction. Right? Because they have a magnitude of 1, and they're each mutually orthogonal. Now, completeness says we need to have all of them for that are mutually perpendicular. It's not sufficient to just have all of them are mutually perpendicular, but we have to have all of the mutually perpendicular ones that exist in that space. And of course, when you have an infinite space, it starts to be confusing. But here's what that means. That means that any vector needs to be something that is composed of a certain amount in direction 1, plus a certain amount in direction 2, plus a certain amount in direction 3, etc. In three-dimensional space, that's where we end. So any vector that I point, this is so much vertical, so much east, and so much north. That's what completeness means. We have all of those different directions. So that any vector we choose can be written as a linear combination of these unit vectors. So this much in this direction, plus this much in this direction, plus this much in this direction.
So is that what the summation thing is saying?
That's exactly what it's saying, yes. So what we have here is called Dirichlet's relation or Dirichlet's theorem or something like that. It's saying that any function, so f of x is any function, can be written as a linear combination. Linear meaning we don't have any squares in here. It's all just psi n, not psi n squared or anything like that, times a constant. So this is, as you said, this is exactly what I was describing for completeness. Any function should be writable as a linear combination of these wave functions. And this comes out in many different ways. I don't know if you guys have studied Fourier series, but that's an example of this as well. And how do we find these little constants out front? Those coefficients are found by utilizing the orthonormal condition. So let me show how that works. So here we have C sub n is equal to integral of psi n star of f of x. Now I'm going to write this as, we had the definition integral of we had that relation, right? And so C sub n is equal to integral of psi sub n star. And then for f of x, I'm putting what Dirichlet said we should be able to do. That is summation. And I'm going to change the index on the second one from n to m because they can't be the same index. I forgot the C. And then finish it off with my dx. Change color. So here I've just substituted for f of x. This stuff here is in red. And then for f of x, I put the function that's in the box there. So this here is rewriting that equation for C of n, and we want to show that this will collapse down to give me just C of n. If it doesn't, we got a problem, because we're basically testing to see if the right side is equal to the left side. So I can simplify this by recognizing C of m and the summation, those can move in and out of the integral. Right? Those aren't functions of x. And so I'm going to have sum over m, C sub m, integral of psi n star, psi m dx. But what is this right here equal to? You want to, but it's this here. It's 0 unless n is equal to m. And so I'm going to write the intermediate of that. So I'm testing to see if C of n is equal to the sum over all m's of Cm times the Kronecker delta Nm. Only one m is going to not have Kronecker delta Nm equals 0. And what's that one m value?
N is equal to m.
Yeah. And so this is just going to be equal to C sub n. Because for all m's not equal to n, it's 0. And so what we've shown is, given this orthonormal relation, that those are a consistent set of rules. So now Actually, I'm not sure if we're going to apply this, if we're going to look at the solutions first before we apply it.
Okay, so I have just a quick question though about the functions.
Yes.
Like, what, I guess I'm just still a little bit confused on why we're saying any other function can be expressed as a linear combination of these.
Mhm.
Like, what would those functions look like?
Well, we're going to do an example. In the textbook, there is, if you look on page 35, it gives an example of, we start our system with at time equals 0. So that's why it says capital psi x 0 is ax times a minus x, which is graphed down below. That's how we prepare our system. And then we're going to say, okay, so that's what psi is. What is psi? So psi is serving the function of f of x in the formula we just did.
Okay.
And so what is psi in terms of our individual solutions? What's the coefficient in front of psi sub 1? What's the coefficient in front of psi sub 2? And that's where we use this set of formulae here.
So that C sub n, that changes for every single integer solution?
Yes.
Of the,
Yes.
Okay.
And that those are determined by how you set up the system. So I'm going to do a different example. I'm going to do a TP example instead of this example.
Okay.
And we'll see what the C sub n's are for that arrangement, for that prepared system. Because, you prepare a system, you have the molecules are at this temperature and this pressure, you set your system, and that's going to set how it starts. Okay, so bringing us back to what our true solution is. We have these individual solutions. We have the time-dependent solution, where here I've replaced E sub n with all the stuff that it is. Time is not part of E sub n, but everything else in the parentheses is the E sub n there. And then our complete solution for the nth state is shown down there. That's our complete solution. And we are always just going to not write this because we know it's there. This is specific to the energies of this system, though. So we have our complete solution. Here's a graph of what the first 4 states look like for the wave functions. Now, in this graph, the colors separate which one is n equals 1, which one is n equals 2, and so on. The vertical spacing is indicating where the energies are. So the lowest one is the lowest energy, n equals 1. N equals 2 is going to be 4 times energy 1. So if you look at the spacing, this here is, if this is 1, then this is 4 from here to here. And then N3 is 9 times because...
to search the web for this year as if this is 1, this is from here to here.
Okay, that's not even supposed to happen. I have the volume turned off unless something crazy happened. Yes, the volume is turned off. I have no idea why she's just getting into the quantum physics, okay? So because the energy was proportional to n squared, that's why the spaces are such. And then these are just showing the magnitude of psi as you go across the packet.
So is that like a graph of the energy of the particle?
No. The graph of the energy of the particle would just be this, or this.
Okay.
And then this here is giving us the wave function, which if we square that will give us the probability density of where we're going to find the particle. Right, so that's not telling us the probabilities yet. We have to square it to get the probabilities. Well, probability density. So squaring it, of course, is very useful to us. You can, I hope, square these in your brain. If you square the bottom one, it's going to be going like that. I should have color coded it. Blue, there. So if you square the bottom one, it's going like that. It's half of a minus cosine wave. And then you square the next one, and it's going to be like that, and so on. And this one has one place that's most likely This one has two locations that are equally, most likely, and so on. For all of them, without doing any calculus, you can answer this question: where is the expectation value going to be?
The expectation is the average.
Right, the expectation is the average.
Right.
So if I take a whole bunch of measurements, where's the average position?
L over 2.
They're all at the center. The expectation value for all of them is right here at the center. Because they're symmetric, well, not actually symmetric, but you have the same amount on each side in every case.
That's interesting. So it's not necessarily like in the middle of the graph, it's just at the point where that line intersects with the graph.
Well, but that is the middle. Right? If we do the integral, as Aaron said, we're going to get L over 2.
Right. Yeah, I understand.
And so L over 2 is where the even solutions cross 0. Where, by even solution, I mean n equals the even number. And so what's the probability of n equals 2 being at its expectation value? 0, because if you square that, it was 0 probability of being at the center. But that's still the expectation value. I always like to point that out to make sure we're really clear that expectation value doesn't mean you're more likely than not to find it there. It means that's where the average is, which is what Chad had specified earlier. So what's the expectation value for position? We could answer that just with a logical argument, or we could have done the calculus. Then what's the expectation value for energy? Well, do you guys remember these were both questions on your test? The last one wasn't actually the expectation value for energy, it was what's the kinetic energy. If we did the expectation value for energy, it's going to be slightly different. If we do the expectation value for energy, well, actually, it would be expectation value of kinetic energy because potential energy is 0, right? So it would come out to be the same, except for, I think one of you did this. You calculated the expectation value for kinetic energy instead of kinetic energy. It comes out to the same value because this is a function of the energy operator. That is, or the kinetic energy operator. The kinetic energy operator acting on this wave function gives us an observable, the kinetic energy times the wave function. And then when you do the expectation value calculation, you're going to have, wow, that came out beautiful. So I'm going to do expectation value of kinetic energy because that's the only kind of energy we have here. And I have to have the time portion if I'm going to do the energy operator because that was ddt. And on both of them. So that's the definition. That's where you always should start for finding expectation values. So I'm going to now change my limit 0 to L because my wave function is 0 outside of that. So the T operator acting on psi sub m is going to give me my energy. I put energy here because, let's face it, we all want to be a little lazy when we do our work. And because we know that we should get E sub n, that's what I put. But I probably should be a little more careful, right? Would you agree? A little more careful would be good. So let's show what that is. let's see, P expectation value of P squared over 2M is equal to expectation value of there. I've expanded the operator for momentum. And so now we can do this. We're going to have it come down to this. Minus h bar squared over 2m times the expectation value of the second derivative with respect to x. Does that all follow? And so let's do the second derivative expectation value. Second derivative. Second derivative means I'm going to bring out the n pi over 2 twice. And it's going to change from a plus sign to a minus sign, so I'll have so the n pi squared or n pi over 2 quantity squared is from taking the derivative. That's L not 2. From taking the derivative twice. And I have the minus sign here because of taking the derivative twice. So bringing that all together in the space that is remaining, minus sign, let me change colors. This minus sign and this minus sign are going to turn into a positive sign. H bar squared, n squared, pi squared over 2ml squared. Hey, look, that is E sub n integral. Oh, I forgot to square root 2 over L here. Integral of 2 over L. Well, I'm going to write it out this way just because it's very clear now. Our orthonormal condition says that that integral has to be 1. We've already established it is. There's no point in going back and doing the integral again and again. And so, indeed, I have the expectation value for kinetic energy is, or for energy is the energy.
Pause.
Pause.
Yes.
So this is all good and all, but like I'm struggling to figure out what kind of questions will come out of this on the test.
On the test, well, you could be asked to show a part of the derivation for the particle in the box, or you could be asked to show that the solutions are orthogonal, or as you've already done, normalize, or what we're going to get to next, not today because we only have 5 minutes left. Taking you have this is how the system is initially prepared. what are the C sub n values? Those are the kinds of things that you have on test. And then there's the knowledge, knowing Dirichlet's theorem, knowing what orthonormal means.
Will we have an example where we have to use the formula C sub n equals integral psi n star?
That's what this example is.
Okay.
So yes. So remember I said, example 2.2 on page 35 is an example of that. And I'm going to work through this. I'm going to obviously do most of the work next class period. But I do have 4 more minutes. So I will at least start out. So what we're saying is, okay, let's say we have a real case. And I'm taking my real case to be an analog to the example of having a string and plucking it at the center. Right? This is an analog to that. When you have the string, you have the waves that go down, you have boundary conditions on that string. It has to be stationary at the ends. So it's very similar in design to what you have here. So our solutions are actually fundamentally the same for a wave on a string as they are for a particle in a box. Then we're saying if you plucked it at the center, how much are you in the n equals 1 state, how much are you in the n equals 2 state, and so on. So that's what we're going to do here. So notice it says normalize this wave function first. It has a in there. A is going to be our normalization constant. And then express it in terms of stationary states. That is, it's equal to blank times psi sub 1 plus blank times psi sub 2 plus, and we're finding all of those C sub n's. So let's start with normalization. That's what we'll be able to get done today. So there I put my normalization condition. I put 0 to capital L because this only exists from 0 to L. So there's no point in having integrals of 0 outside of that. And so now I have to put in my function, and notice I have 2 regimes, so I have to break it into 2 different integrals. Integral from 0 to L over 2, and then my psi there is going to be AX. And my, plus integral from L over 2 to L. And now my function is so I have these 2 integrals, or if you prefer, we can make them more integrals. I prefer, by the way, just in case you. So I am going to write these as simplified as I can. This is a mod squared integral from 0 to L over 2 of x squared dx plus a mod squared integral from L over 2 to L of L squared minus 2Lx plus x squared dx, where I expanded L minus x times L minus x. Are you with me? Chad? All right, so the integral of x squared dx integral of L squared dx, that's pretty trivial, right? L squared x minus 2L x squared over 2 plus x cubed over 3. And now we just have to put in our values. A mod squared And now I'm just going to factor a mod squared out from everything because everything had a mod squared in it. That's going to be L cubed over 3 times a is 24 minus 0. That's my first one. And then plus L cubed minus L cubed over 2. That's putting in the upper and lower limits for the first term.
Did you put it?
Yeah, so that was an interesting looking cube, wasn't it? So going to the next one, I have minus 2 L cubed over 2 plus 2L. Okay, 2 over 2, I'm not going to write that. That's ridiculous. Plus L cubed over 4. So these are that. And then finally, plus L cubed over 3 minus L cubed over 24. And I curved up as I was going across. But we can now see that this and this add to 0. And what we're left with then is, and this also add to 0. And this add to 0. So what I'm left with is a mod squared times L cubed over 4 equals 1. Therefore, A is equal to 2 over L to the 3/2 power. Hopefully I made no mistakes here.
The L cubed over 2 and the L cubed over 3. Just cross out.
I thought they were the same. They're not. Okay. Then this is wrong. Okay, I went 3 minutes over our agreed upon time. I will straighten that out beginning next class period.